think this is the official start of 165, 265. I told you this is the first engineering class spanning all of the different departments. So that's a novelty here at UC Irvine. Today is the first class, so there's a little bit of repeat of what we told you about yesterday, but just for you.
Thank you.
We'll redo everything. So we are talking about advanced manufacturing choices. That means it's not only about additive manufacturing or 3D printing. It's basically to give you an insight in all of the different options we have to make something, to physically make an object. And by the end of this quarter, you should be able to make an intelligent choice. When you get a design, some specifications, you can figure out what is the optimal approach to manufacture that thing. So you already have one challenge that you got the other day. It's making that cradle for your cell phone, right? On Monday, you'll get much more detail on how to tackle that problem. But so let's get started. So advanced manufacturing processes, we can tackle them by considering the energy you use to work on the workpiece. The workpiece is the object you want to craft into something. Now we can apply different kind of energies to make something. It can be mechanical energy, such as cutting and shaping. It could be electrical energy. It could be heat energy, such as in laser cutting. Or it could be chemical energy, such as in electrochemical machining. If you look at this object here at the bottom, this is a human hair. Now we can see there's square holes in there. You should be able, at the end of this quarter, to tell us how was this done and how would you do it. By the way, what's the diameter of a human hair?
Oh man, I think it's 15 microns.
You have very thin hair. It's between 80 and 100 microns. And so, to give you already a little bit of a feel for things, if you do make something mechanically, let's say drilling, a good rule of thumb is this: 100 microns is about the smallest drill you'll be able to use. So if you have an object that you need to make with grooves in it, and it's say 15 microns, or it's like this, I promise you this is not made with a mechanical drill. It's one of the other techniques. We're going to learn what techniques that would be, how you could make holes of that kind of precision in a human hair. By the way, this categorizing here in these four energy domains is not always that straightforward. We will often see that things are a combination. For example, it will often be chemical energy and heat energy, especially in cases where you consider additive manufacturing. So that's another kind of distinction I'm making now. 4 energy fields to characterize manufacturing, but then there's yet a bigger kind of division between manufacturing entities or groups that is additive versus subtractive. Now additive, the word says it itself, you add layer by layer, you build up something, you add to it, additive manufacturing. This, on the other hand, is subtractive, so you're taking things away. So probably you will be asked at one point the question, laser machining. In what energy domain does that fall? And is it additive or subtractive? We will actually see that laser machining can be both. You can deposit something, add something, or subtract something with lasers. So already 2 ways of looking at manufacturing in terms of the energy that you apply to a workpiece and in terms of it either being additive or subtractive. So these are the kind of things I expect you people to be able to do after you go through this set of classes. You will be able to decide when to apply mechanical machining versus lithography. I already gave you a little bit of a hint on that. Remember I said 100 microns is about the cutoff. You know, if you have an object that's 15 microns, 2 microns, pretty much forget about mechanical machining. Lithography might be an option. We'll see there's quite a few other options. Then, what type of mechanical machining will you decide upon? Because within the mechanical machining group, we'll see, I'm only going to give 3 or 4 examples, there's many more. But so you're going to be able to say, I'm going to use that kind of mechanical machining. And then if it's lithography, what type of lithography will I use? There's electron beam lithography, photolithography, and on and on and on. So you need to have a little bit of an idea which one to choose. 3, when to use bottom-up versus top-down manufacturing. I already gave you a hint on Monday what that is all about. Mankind mostly has developed objects by cutting things down. That's top-down, from a big block of material, let's say a big bowl of silicon, going to an IC. That's definitely top-down. But more and more, the last 10, 15 years, we are now able to build things, actually grow them, in a chemical vat. And that's bottom-up. That's actually how nature built things. And actually, it's kind of interesting nowadays, the size of objects one can make with either means is starting to overlap. That means you could actually get to that size by making something smaller and smaller, or by building up something atom by atom. So we are living in a very interesting time that that is possible, that we have that choice. 4, and we're going to talk more about that today, it's a very simple introduction, and it's yet another way of categorizing manufacturing, that is, choose a serial, batch, or continuous manufacturing method. Then 5, what the rapid prototyping method select. So be there on Monday, because on Monday, that's what we're going to be talking about. You're going to be explained what kind of machines we have at Rapid Tech, and which one to choose for what purpose. Is it metal you're going to be working on, ceramic or plastic? You're going to be able to choose what 3D printing machine to use. This eventually will lead to a logical decision tree that we will present to you so that you can help sort out what machining option to choose. And examples will include a variety of products ranging in size from nanometers to centimeters. Actually, even bigger than centimeters. There's a wide range of objects one can manufacture. By the way, I need to tell you a little bit about that. Nature is much better at manufacturing in a much wider length scale. If you look at a tree and the sizes of objects that you find on a tree, you're going to go from literally molecules to 15 meters for a tall tree. Think about human manufacturing. There's not one object that mankind can make that has so many length scales. So it's really intriguing to consider manufacturing in a broader daylight and see if in the future we'll be able to make things in many more length scales. Probably a typical product that we make will have 2 orders of magnitude or 3 orders of magnitude in size. Whereas in nature, like in the case of the tree, you're talking about 21 orders of magnitude. So we have a lot to learn, and that's, by the way, one of the reasons why we are looking at this bottom-up manufacturing as a possibility for the future. This is a little bit of a silly video, but I'm going to play it anyways. It's about the size of things, because I just talked about this power of nature to make things in many different length scales. If you go on YouTube, you'll find plenty of them. But this is kind of a nice one. It gives you an idea of size. Like when I was asking you about the diameter of human hair, you have to kind of get an instinctive feeling for that. What's the size of these objects? By the way, as humans, it's very easy for us to estimate the size of a door, a hand, but when things become very small in the nanometer scale, people are pretty much lost. They don't have a good intuition for that size. And that's why maybe looking at a little movie like this.
In the past, there were scientists who studied the stars and scientists that studied atoms. And even today, there are scientists called cosmologists and scientists called particle physicists. Yet there is a direct connection between the physics of the very large and the physics of the very small, because even the largest objects in the universe are made of exactly the same building blocks as the smallest things. Measuring things is at the heart of science. One of science's great achievements is to have accurately measured everything from the size of the universe to the size of the tiny particles that make up the heart of an atom.
Diameter of DNA?
2 micron?
Oh, 2 nanometer. Microns.
To be way off.
I will refer back to this movie in a little bit when I start talking about relative tolerance versus absolute tolerance. So keep that in mind.
Questions that all physicists want to answer.
So, syllabus. And the first topics we're going to cover today, 1 and 2. We're going to tell you about sealed batch and continuous manufacturing processes. Probably I almost could point at someone in the audience and you would be able to tell the difference between those three. But importantly, we're going to talk about relative tolerance versus absolute machining tolerance. And we're going to find some surprising things. People that are from the IC world think that the best relative tolerance can be achieved in making integrated circuitry. And you will find that's not true. You will actually see that the best relative tolerance is achieved on things that are the size of a human hand. But I'll come back to that in a moment. Then, third topic, and I think we will start with that also today. I think I can start with mechanical energy today. I'm going to talk about cutting, shaping, forging, ultrasonic machining, and sputtering. Examples of mechanical energy application, right? Then another group of manufacturing processes use electrical energy. And there we'll talk about, as an example, EDM, electrical discharge machining. Yet another category or heat energy, laser machining, plastic molding are examples there. By the way, all of that is on the web, right? So you know where to find that. Then yet other, group 4, is chemical energy. And as an example, we'll deal with electrochemical machining, ECM, and chemical machining. I will then cover in one class next generation lithography tools. We'll talk about nanomachining tools, top-down versus bottom-up machining, rapid prototyping, which is class 10 is actually what you will be getting on Monday. And then the practica, of course, will directly flow out of class 10. Then 11 is kind of, you know, coming towards the end of the quarter, matching manufacturing process to product specification and design. That will be in the final. You will get such a problem. I will ask you an optimum manufacturing technique for a certain design specification. And then we'll talk about the manufacturing process decision tree. So that is the syllabus. And now finally, class 1. So many introductions, right? So in class 1, we will give you a definition of manufacturing. We're going to make it very easy. We're going to go to Wikipedia. Pretty much everyone does that, right? We're going to see what Wikipedia tells us manufacturing is. And then the difference between sealed batch and continuous manufacturing processes, and the difference between relative versus absolute machining tolerances. Here you have again kind of one of these cartoons that's often used in manufacturing. And this one is used to point out that there's a gap in manufacturing capability between the silicon micromachining area and then the mechanical machining, miniature machining. In between here is a gap that's very difficult to fill. There's very little tools, manufacturing tools, that can easily bridge the gap between an integrated circuitry and a bigger container box, let's say the packaging. So that's actually a very good field to be in. We call it meso machining, between silicon micromachining and miniature machining. But so here we go. We can read it together. A lot of people would say there's too many words on there, but so I'm going to ask someone in the audience to read it aloud.
Manufacturing is the use of machine, tools, and labor to make things for use or sale. The terms may refer to a range of human activities from handicraft to high-tech, but it is most commonly applied to industrial production, in which raw materials are transformed into finished goods on a large scale, such as finished goods may be used for manufacturing. Other more complex products such as household applications or automobiles are sold to wholesalers who in turn sells them to retailers, who then sell them to end user, the customers.
The consumers, okay. What does it basically say? What is manufacturing is? Translate that, because there's a lot of words there. Can you translate that? What is manufacturing? Come on, be brave. Oh, see, he's more shocked than you. And this is all on video, huh? It's going to be on YouTube tomorrow. Try it anyways. He's crying. What happened? Help your friend, help your friend. Come on. Summarize this, because there's too many words there, right? If someone asks you in a casual conversation, what's manufacturing? Come on, you do it.
You use machines and tools to make something who someone else, or you're going to transform a raw material into something that someone's going to buy.
Yeah, and you know that the wealth of nations is principally built on that. That's an important lesson that people are learning, that manufacturing something is what keeps nations healthy and keeps a good middle class working. It's a very important point. And by the way, what's also in there, it's not only making product, but also the machines that make products. These are the tools. And the tool industry is something that's become very weak in the United States. And you see, if you control the tools, you control the next generation products. There's actually some manufacturing equipment, for example, by Fanuc from Japan, that is not brought to the US anymore. Because they say, because it's so expensive to send trainers on that equipment, but also probably it maintains a huge advantage in Japan. If you have a better tool-making gear, your economy will be better off because you can sell products that others cannot. That's why we are having this class about advanced manufacturing equipment. Maybe some of you will come up with new tools. Actually, one of the classes, you will have one of my students, Julia Canton, talking about near-field electrospinning, a technique that was invented here at UCI, that they want to commercialize. And if we could do that with this team, we've really fulfilled an important task, building new manufacturing tools. Okay, so here comes a very simple segment of the class. This is the serial versus batch versus continuous. Let's do this together. What is serial manufacturing? Well, you make one object at a time, right? And that's how it used to be, right? You would have someone on a lathe, on a CNC machine, one object at a time. A lot of work, very expensive. The next one, well, is batch. Now, the prime example of a batch fabrication process, what would that be? I think all of you know it. What is the best example you could think of a batch fabrication process? Say?
Cars.
No? Chips, integrated circuitry. Because what do you do in batch? In batch, you have on one substrate perhaps 600 devices that are all made at the same time. They're all identical. That is what has caused this dramatic revolution in the electronics world. The fact that instead of making one transistor at a time, I built thousands of circuitries, transistors, all at the same time. That wafer, with all of these processed ICs, only went from station to station when the previous step was done over all of the devices, batch. What's yet better than batch? Continuous. Now you all know an example of continuous manufacturing. Newspaper printing. You have a roll that feeds the paper into the pickup roll, and you make continuous product. Be it Time magazine, be it a newspaper, that's continuous manufacturing. We will learn that there's a lot of people in research trying to bring manufacturing process from batch to continuous. An example is in the integrated circuitry. Many of us have tried to apply integrated circuitry to making biomedical devices. You know, let's say a glucose sensor. But you know what you find out? It's too expensive. Because pretty much the least expensive device you'll make on silicon will still cost about $0.50. You know how much a glucose sensor strip costs for diabetics? What do you think? 10 cents. And how can you make something in such mass unless you do it continuous? So there's a lot of thinking going into how could I, for example, make integrated circuitry continuously rather than in a batch, wafer by wafer. So continuous production is a method used to manufacture, produce or process materials without interruption. And the primary characteristic of batch production is that a group of identical components are completed at the workstation before they move to the next one. Example, IC fabrication. For example, you do a sputtering step, all of the devices on that wafer are coated at the same time, they are very identical. Now I move on, perhaps to an etching step, that's batch. So let's look at an example of serial. This man is making a ski. So making skis, that will be definitely serial process. You make one at a time. You can find many other examples, right? And this then, here, on the left, is an example of batch fabrication. And then on the right, you have a continuous fabrication. And a continuous fabrication means you will always have something called a web that continuously moves, and while the web is moving, you do something on the substrate of that web. So how many different ways have we already learned in this short amount of time on how we can characterize manufacturing? Think back. 1, 3.
Energy.
Yeah, so energy. Yeah, so that's one. Characterizing them by energy applied to the workpiece. The other one was?
Additive and subtractive.
Additive, subtractive. And now?
Serial batch.
Serial, batch, continuous. So you can already start feeling that there's quite a bit of order to be created in this dramatic number of manufacturing processes. And by doing this in this class, I think you'll be able to kind of weave your way through all of the different methods available. Not much more difficult, but you'll have to put on your thinking hat a little bit because there will be a surprising outcome here. This is where I come to this point of relative versus absolute tolerance. So a dimension is a numerical value expressed in some units of measure and used to define size, location, orientation, etc. Right? So let's say we'll call that dimension there centimeter, microns, I don't care, it doesn't matter. A tolerance now is the acceptable variation on that dimension. And what is the relative tolerance? The tolerance on dimension over dimension. Okay, what does that mean? That last statement. And so here, you see plus or minus 0.25, let's say microns. That's the acceptable variation. Now, if I divide 0.25 by 12.25, I have the relative tolerance. Another example, you have 100 centimeter and your tolerance is plus or 1 centimeter. What is the relative tolerance? 1%. 1%. Why is that important? Well, mechanical engineers, you know, they will only call something precision engineering if the relative tolerance is better than 10 to the minus 4. Now, we will learn that in integrated circuitry, you're actually lucky if you have 1 to 5%. And that's a surprising thing. So hold on, and I'll show you a curve, and I'll interpret that curve with you. I'll come back to this slide in a moment, but the curve I want to explain to you is the one here. And so follow with me, it's the only thing that requires a little bit of deeper thinking this class today. What I have plotted there on the x-axis is relative tolerance. So you see 10%, 1%, 0.1, 0.001, and you can see precision machining, there's a line here that's at 0.01 or 10 to the minus 4. right? So mechanical engineers will call something precision engineering only when the relative tolerance is 0.001. Now what's on this axis is the size of the object. So I start with a huge thing, a temple, 100 meters, and I end up with something very small, let's say 1 micron. And what you see is that as a function of size, the relative tolerance goes over a peak. In other words, the relative tolerance is poor for very big things. It's very poor for very small things. Do you have an instinctive feeling why that might be? It's a very important insight. It's so cute once you get it why it is. And you know what the optimum is? Look, you can go to 1 part per million. For an object, that's the size of a human hand. It's really neat. What do you think is behind that?
Did gravity dominate when you are on the large scale?
Say it.
Gravity, like weight,
Well,
and then molecules.
it has to do with your XY stages. Look, have you ever seen a good XY positioning stage for a temple? Would be very difficult, right? If you have a huge dimension, you know, you have to be correct over 100 meters. Or you're building your house. You know what the relative tolerance will be if you build your house? Look at it. Actually, I'm specifying it. Relative tolerance for building a house is about 1%. Eh? Yeah. Yeah, more to maybe 2-3%. That kind of feels right, right? And if there's a bigger thing, your relative, you will be more off because it's more difficult to measure it. It's not like you can put it like the size of a human hand on a positioning stage, which you can measure very well. Eh? Now the same about small things, and I'm going to challenge all of the people that are in nanomachining and micromachining, including myself. We used to say it's the best out there. It's the best for making very small things. But in terms of relative tolerance, I tell you, try to make a 100 micron line of silver, and if you have it 101 or 99, you'll be pretty happy, no? What does that mean? Relative tolerance of an integrated circuitry is about the same as you building a house. It's a very important insight. It means that often actually, if relative tolerance is important, you better make the thing bigger. Making it too small means that your relative tolerance will not be so good. Do you get that? It's an important point for this class. So lithography, for example, silicon micromachining, is excellent for small absolute tolerances, right? So yes, if you want to make very small things, you're not going to do it with mechanical machining. But if your relative tolerance is very important, ultra-fine diamond milling is better. So people that have been polishing these mirrors at JPL for NASA, the relative tolerances of these things are much better than on your IC. In some cases, and that's the point I was making, we might want to keep our micro machine, make it a bit more macro if relative tolerance is important. Right? So always remember kind of that curve and where it comes from. The points on the curve are from practice or from examples. Right? There's no law exactly describing that. There's no physics that I could put up there that would tell you the shape of the curve needs to be like that. Very good. And so now I'll go to the slide that came before, which is also a very important one and also will carry a lesson for you. What we look at in this curve, I'm sorry it's a little bit small print, but you guys are young, you have very good eyes, right? No? I'm going to go through it with you, okay? You understood the previous curve. Everyone understood that one, the bell-shaped curve? Are you all okay with that? Yeah? Okay, so let's try to interpret this one. What I'm plotting here is the year from 1900 to 2020. What's on the left is achievable machining accuracy. And on the right is the number of transistors on a DRAM. Now you can see that the number of transistors as time goes on becomes bigger and bigger because I can make things smaller and smaller. So in other words, the fact that this curve goes up is only because it's the number of transistors. It's 1 over, right? But so you make smaller and smaller items. The three curves that have normal machining, precision machining, and ultra-precision machining, or what mechanical engineers choose to determine the different ranges of mechanical accuracy. And you can see the ultra-precision machining, extreme accurate machining, was the one that we were referring to a moment ago. That's here, all the way at the tip of the curve. The most accurate thing you can make. That is with this ultra-fine diamond machining. Now, the question I'm going to ask, and that I want you to reflect about, is this. These curves going like this is mechanical machining, right? And that curve going like this is in the IC world. What's the commonality between these two? What's driving the progress as a function of time to make things smaller and smaller and better accuracies are achieved? And it's the same thing that controls these curves for integrated circuitry or for mechanical machining. What do you think it is?
You can position them better.
Exactly. It's the XY stages, a positioning stage. The most important invention, in a way, for both mechanical machining and manufacturing anything and integrated circuitry is how good you can control the position on an XY stage of the product you're making. And so as time went on, position stages got better and better. We got rid of any vibration, we got air bearings, and the better that got, and the better we could control the smallest dimension change on these stages, the better product we could make. So there is not all that much difference, in a way, between integrated circuit manufacturing and mechanical machining, because both are grounded in the need of very good XY positioning stages. By the way, I will come back to this graph later on in the course, because here on the right, it tells you all of the machine tools to get to these smaller and smaller dimensions beyond the mechanical machining. And it also tells you the metrology equipment you need to measure. Everyone knows the word metrology? So metrology means the measuring equipment of the devices we're making. And so it gives machine tools on the left side in that table and measuring equipment on the right side. But that table will come back in a later class when we are a little bit more advanced, where we've seen more examples of manufacturing tools. This is the last slide from class 1, so we're gonna making good progress. We're gonna get into class 2, so we're gonna start with some mechanical machining examples. What this shows you, and you probably kind of can expect this is the cost of a device. In this case, it's stainless steel. You're making something out of stainless steel as a function of the tolerance, the fineness of the shape you're making in that stainless steel. And as you can expect, as the nominal tolerances decrease, the cost really shoots up. And so you will see that molding something, CNC machining, has a certain cost, but it's relatively low compared to you having to polish it. The finer the steps, the last steps, the bigger the expense of the object you're making. Very good. So that was the first class, and let's go on to class 2. Okay. I won't finish this class, but I think I can get into the material somewhat. So we're going to start with considering some mechanical machining. And so typically what will be involved is some mechanical force on a workpiece. In this case, we have a tool that's harder than the material we are working on, and it chips away the material into the shape we want to make. The things we will cover in this class are as follows. We start off with yet another way to categorize manufacturing. Number 4. In this case, we're going to talk about primary manufacturing, secondary, and tertiary manufacturing. And thinking back about that last graph of class 1, you can see that primary, secondary, and tertiary will also relate to the cost of the object. Tertiary will be fine polishing, much more expensive than primary. So, fourth way of categorizing manufacturing processes in terms of primary, secondary, and tertiary. What that is, you'll see in a moment. We'll give a definition of mechanical machining, and then 4 recognized categories in mechanical machining. It's turning, milling, drilling, and grinding. And so it will be easy to figure out what drilling and grinding is. Turning and milling, you'll always be confused. You always flip it around. So make sure you don't flip it around. In one case, your tool is turning. In the other case, your workpiece is turning. Okay? But we'll give you little videos to get an idea of each. Then we'll go in more detail on CNC machining. Who knows what that CNC stands for? Does anyone know what that is? What does it stand for? CNC? Yes?
Computerized numerical control?
Yes. And so we'll tell you where that name came from. We'll talk about precision machining, ultra precision and nanotechnology. That's going to refer back to these curves. Because you know, nanotechnology, the word did not come up from the IC world. It came up from the mechanical machining world. You can now, with mechanical machining, very well reach the nano domain. That's shocking to many people. But the nano domain you reach with mechanical machining will only be in the z-axis. It will not be in the xy axis. You cannot understand that yet, but remember that. It's a very important point. And then finally, we will talk about desktop factory. I'm not sure that I will get to that this class, but definitely on Thursday. Desktop factory has been heralded by some people as maybe the solution to the problem of outsourcing manufacturing. The idea came about, interestingly enough, in Japan, because they were losing manufacturing faster to China than the US used to lose manufacturing to Japan. They got alarmed. What do we do? And the idea was, well, suppose that a manufacturing entity can sit on your table. And this is not only, at that time, they were not thinking about 3D printing. They were truly thinking about little stations that would have basically a train set that brings in a material. In that little desktop factory, some machining goes on, maybe some drilling. Then that train goes on to another desktop factory where there's some gluing going on, etc. There were no humans into these desktop factories at all. So everything was done robotically, and the pieces were brought from station to station. I will give you some examples. There's some companies like Sankyo Seiki, Olympus, who has some of that equipment. To me, it still represents possibly a future where, in a way, factories become much smaller, decentralized. So instead of these tremendously expensive IC labs or huge concentration of automotive manufacturing, there will be distribution of manufacturing so that many more people can invent, make things, and perhaps spread the wealth. Right? So desktop factories, that's the last point for this class, class 2. This is again a little bit philosophical, and people are all now looking, they're afraid who is going to ask to read this. You have a good strong voice, right?
Me?
Yeah. Okay, so manufacturing. Loud.
Manufacturing dominates world trade. It is the main wealth creating activity of all industrialized nations and many developing nations. A manufacturing industry based on advanced technologies with the capability of competing in world markets can ensure a higher standard of living for an industrial nation.
Very good. So that kind of comes to this point, right? People think it's about oil you have in the ground or some minerals. Not true. It's actually about how educated your people are and how good they are at manufacturing new products that are sold to other countries. And we need to get back there. Second bullet point, okay, I'll read it, but you did a good job, okay? So primary manufacturing processes involve casting and molding. What is casting and molding? By the way, there's a difference between casting and molding, but most people don't really obey the rules. You know, if you read it, you'll see they flip it all around. But casting is basically when it's disposable. After you created the shape, you get rid of it. For example, sand casting. You make a shape in sand, pour metal in it, and obviously then the sand will be getting rid of. That would be sand casting. A mold is when you can use it again. Okay? So, but in both cases, casting or molding, what is it? It's the act or process of making casts or impressions or of shaping metal or plastering a mold. The act or the process of pouring molten metal into a mold. So that is primary manufacturing, the least expensive, right, of the three. Secondary, where are we? Oop. Oh, secondary manufacturing processes constitute the main mechanical removing techniques. So, for example, the mechanical CNC machining, turning, milling, that's secondary. And then tertiary is abrasive, is polishing, is fine-tuning it. So we're going to start by looking at a movie that's a very good example of casting. But first, before going on, so the difference between casting and molding is that in traditional casting processes, the mold is destroyed. For example, here you have sand casting on the top. I will not show a video of that. You can Google that, but you can kind of get the picture, right? You make an impression in sand, then you pour the material into that impression, and voila, you have made your product. But the one that I'm going to show you is probably one of the mainstays, maybe the most important one, which is called the lost wax casting process. So follow this video carefully. It's kind of one of the main manufacturing processes today. Lost wax casting process, a primary manufacturing process. So here we go.
Many machine parts are simply stamped or machined out of solid metal. But parts with complex shapes or thin walls can't be made that way. They have to be cast using a technique called lost wax process casting. It takes anywhere from a week to a month to manufacture a cast metal part, depending on its complexity. The first step is to inject wax into an aluminum die, which is essentially a mold whose cavity is in the shape of the part. This creates a wax model slightly larger than a finished part will be. They'll use this wax model to make a mold out of a ceramic material. The mold has to be larger than the finished part because metal shrinks as it cools. Once the wax model is ready, they stamp on a code to tell the foundry workers what type of metal to use when they cast the part. Next, using a hot iron, they attach wax components to create what's called a metal delivery system. Channels that will funnel the molten metal into the mold's cavity. Next, they dip this wax assembly into a ceramic solution called slurry. They do this by hand to prevent imperfections that would cause defects in the casting. To strengthen the slurry, they coat it in a fine zirconium sand, then let it dry. A robot then keeps repeating the process with coarser sand until the ceramic shell surrounding the wax assembly is about 3/10 of an inch thick. This takes 5 days. Now the ceramic-covered wax assembly is ready for what they call the de-wax. Workers place it in a hot steam chamber called an autoclave for 5 to 10 minutes. This melts the wax right out of the shell, creating a ceramic mold whose cavity is in the shape of the part. Once the mold is dried out, workers can begin to cast the part. First, they put the cold mold into an oven and heat it up for 2 to 3 hours. This prevents the mold from cracking from shock when it comes into contact with molten metal that's close to 2200 degrees Fahrenheit. They pour the metal into the mold's cavity, then let it cool and harden at room temperature. It takes 2 hours for aluminum, 4 to 5 hours for steel. Once the metal is cooled and solidified, they break off the ceramic mold using a vibrating hammer. This takes about 5 minutes. They saw off the metal delivery system. Then grind the surface smooth. The final step is to make sure the part came to the exact dimensions specified in the technical drawing. This is called sizing. Steel parts have to be heated up in an oven for sizing. Aluminum parts are sized cold. Technicians use a series of tools and presses to measure the part. If it doesn't meet specifications, it's either reworked or simply discarded. They use sophisticated equipment such as this optical comparator to check the angles and radiuses, and this coordinate measuring machine to verify dimensions. Lost wax process casting is used to make metal parts for all types of machines and equipment, everything from military weapons to snowmobiles.
Okay, so that was rather fast, right? Should I play it again? Let's see how much we got out of it. Is this additive or subtractive process?
Additive.
Additive, right? Now, there were two molds in there that are both lost. What are they?
Ceramic and wax.
Ceramic and wax, right? And why do we go in these two steps? Why do we go in these two steps? Why did we go from wax then to ceramic?
Make a negative imprint first.
Yeah, because it's easy to pour the wax on your metal original, the master, so to speak. Huh? So you should make sure that you at least once watch that video on your own and make sure you understand each of the steps. It's a very important process, the lost wax casting process.
What type of wax is that? Is that a special type of wax, or is it like candle wax?
It's just like candle wax. In a way, this technique is so old, you know, even the Egyptians already used wax molding kind of techniques. And in a way, in lithography, soft lithography, etc., is also based on that same principle. So this is definitely nothing new. So now a little bit more about mechanical removal techniques. So what was that? That was an example. The sand casting was an example of primary machining. Right now, CNC machining, mechanical machining, is a secondary technique. So in mechanical removal processes, stress is induced by a tool overcome the strength of the material. We saw that we had a piece of metal and there was this chipper, a tool, taking off chips of the workpiece, right? So obviously that tool needs to be stronger than the workpiece. The process produces complex 3D shapes with very good dimensional control and good surface finishes. Now, point 3 is very important. This is extremely wasteful, and that is why this additive manufacturing and 3D printing has become so hot, you know, because if you do subtractive like we do here, there's so many wastage, so much energy that you have to put in to create that shape. If on the other hand, you have the powder and you laser together the powder in the shape of what you want, there's no loss at all, because all the powder that's not used, you can use for the next piece, right? So third point, the method is wasteful of material and expensive in terms of labor and capital. How well a part made from a given material holds its shape with time and stress is referred to as the dimensional stability of the part and the material. And this is one of the reasons why you do machining. You have to be careful that, for example, your drill doesn't run too hot, because you might actually create something that is called a heat-affected zone. I'm already announcing this word now. It will come back many times. HAZ, heat-affected zone, is a very bad thing to have in manufacturing. Because the heat-affected zone, the material gets so hot, it actually changes property. And methods that avoid the heat-affected zone are often preferred. And so that will be one of the criteria. If in a question, you know, I'm asking to make sure that there's no heat-induced stress on that object, you will avoid techniques like this. So don't worry, I'll come back to that, but do write it down already. HAZ, heat affected zone, important concept. To maximize dimensional stability, the machine design engineer tries to minimize the ratios of applied and residual stress to yield strength of the material. A good rule of thumb here is to keep the static stress below 10 to 20% of yield strength. Then you're safe. Increased heat at the workpiece, I was just talking about that, causes uneven dimensional changes in the part being machined, making it difficult to control its dimensional accuracy and tolerances. Thermal errors are often the dominant type of error in precision machining. And thermal characteristics such as thermal expansion coefficient and thermal conductivity deserve special attention. That's where people like mechanical engineers come in. They understand how fast the heat can dissipate in an object, so how fast they can drill. Machining, manufacturing is too often considered something for the dirty back room. It's not anymore. It's very sophisticated. We need for the future people that can manufacture because they know the physics that's involved. Okay? So to show that also mechanical machining has been around, not only casting, this is 300 BC, a drawing made on a wall in Egypt. And what it shows in this line drawing, the man on the left is holding the cutting tool, so he has something that's harder, and he's holding it. And this man here with this rope is making the workpiece turn, right? In other words, they will make a cylindrical object here and machine it with this tool. So the man at the right is making the workpiece rotate back and forth by pulling on a cord or tongue. So nothing really new, right? And you can see how intrinsically it's linked to culture and advance in a society, finding new ways of making things. In mechanical subtractive machining, you understand each word now, right? Mechanical, because it's a mechanical force I apply, and subtractive. Physical removal of unwanted material is achieved by mechanical energy applied at the workpiece. Mechanical material removing technologies are also categorized as single-point machining or abrasive machining, which is multi-point machining. Case in point, you can have one sharp object, maybe a diamond tip, that single point to machine a very small groove, or you can have sandpaper with many points to polish something, right? That would be multi-point machining. Method number 5, right? To identify manufacturing, single point, multi-point. So keep track of those, because one good question would be, I'm giving you a machining method, and then you categorize it according to all of these criteria we are building up here. Mechanical removal processes, we said already, can be broken down in turning, milling, drilling, and grinding. And that's the last thing we're going to go over for the class today, and we'll illustrate each of these processes with some videos. First, some definitions. What is milling? It's the use of a rotating multi-point cutting tool to machine flat surfaces, slots, or internal recesses in a workpiece. So when you've seen these CNC machines and you see basically a cabinet with a plastic wall, and you see water hitting the workpiece, and you see a tool that can move in the X, Y, and Z direction, and on top of that rotate, you know you're looking at a milling machine, a CNC machine. Milling is one of the more versatile machining processes. There are 3 degrees of freedom associated with milling. Now the tool can move up and down, left to right, and front to back. Now, when you're going to buy a CNC machine, it's going to be a 3-axis, 4-axis, or 5-axis. I wonder if someone would already have the foresight. There is no 6-axis machine. So think about it, right? This way, right? This way, and then rotating around this axis. That will only lead to 5, not 6. If you don't understand it yet, I'll have a drawing a little bit later. Do you know why? You'll get there. Sorry? You're mumbling. Okay, we keep the suspense. Huh? If you don't figure it out now, we're going to start with that on Thursday. Or someone will raise his or her hand. I know it. I know why there's no 6-axis machines, only 5-axis machines. As soon as I show the drawing with all of the orientations, of course, because there will be one that's identical, right? Doesn't make a change. So the tool can move up and down, left to right, and front to back. In this process, the tool spins while the part remains stationary. While as in turning is the machining operation that produces cylindrical parts. You remember the Egyptian, right? There was the workpiece that was rotating, and the tool was stationary. Milling is just the opposite. So let's watch a movie of each of these operations, and then call it a day.
Okay, the basic roughing technique, what you want to do with your tool is start with the tool where it's above. Let it go till you just start hitting.
So what is this?
Then bring the tool down and pull it back until you start cutting.
Turning,
what
right?
it will look like, start above, you just start getting seeing chips come off. Start at one end and make yourself small cuts. You want to try to use as much of this edge as possible.
That's not too bad. Okay.
Bring yourself down.
You should all do it. It gives you some pleasure. Making things is actually fun.
You take small shots, small cuts, all the way from the front end, all the way to the back of the wood.
Of course, now you're going to laugh.
When you go to the opposite direction, rotate the tool over. And then use the other side. Once in a while, I'll just move it back and forth, or you can rotate it, whichever is most comfortable for you.
Next. So now this one. You tell me what this is. CNC, yes, and the process. Milling, right? And by the way, this is Haas. This is one of the big manufacturers still of these CNC machines. And so in the CNC class, you're going to be told how to operate one of those, right? How much do we think a station like that costs?
50 grand.
What?
50,000.
50? Yeah, it's more in the hundreds. And then finally, kind of as a little funny ending for this class today, drilling can be defined as a rotary end cutting tool having one or more cutting lips. So I have a drill, and you've been drilling, right, to hang pictures up. And there's flutes there so that the material that you drill away can escape. And here I'm going to show you a primitive example. It's a MacGyver finding himself in the forest, and he needs to make fire. Okay, so. So what is he doing? No, he's not cutting that twig. What is he doing? He's making fire, right? I told you how basic manufacturing was, right? There we go. Where there's smoke, there is fire. Who has ever done that? Higher, higher. 1, 2, 3, 4. Like this? Did you do it like that? Okay, so this is running its course. I will all see you on Thursday.